In this lesson, we're going to be extending our knowledge of tangent lines to explore and apply a relationship between two tangent segments that are drawn from a common point outside the circle. So, of course, we've talked about before that tangent segments only intersect the circle at one point, and they have to be outside the circle because of that. If they went inside, they would eventually cross a second time. So let's look at questions 1 through 3 in your notes. It tells us that when a GPS satellite system is designed, the scientists want to minimize the number of satellites they use and the distance that the transmitters need to send the signals. So they want to cover the maximum amount of area on the Earth with as little satellites as possible. So in this diagram, S is the orbiting satellite, C is the center of the Earth, and SE is an altitude of the satellite. So that represents its height from the Earth. Arc AEB is the arc along the surface of the Earth that the satellite signal would reach. So we know this is the area of the Earth that would reach the signal. We're using 4,000 miles as the radius of the Earth. And so our questions that we're not going to solve today, we're just going to be talking about how we would go about it, says if a satellite is orbiting at 15,000 miles, so what is that giving me? That's giving me the height the satellite is from the Earth. So remember that's segment SE. It wants to know what percent of the Earth's surface would its signal reach. So we know the entire Earth, if we just look at the circular arc here, would be 360 degrees. So we would need to know what the arc AEB has as its measure to figure out that percentage. AEB would be our part, and of course 360 degrees would be our whole. Part B says if a satellite signal reaches 45% of the Earth's surface, what is the orbiting altitude? So it's kind of taking part A and asking a reverse type problem. What if they give you that AEB's arc measure is 45% of 360? Then could you find the length of SE? These are some questions that we're going to answer 1 through 3 on our notes. So it says, what kind of triangle would we know ACS to be? So remember, we have already learned that these are radii of the circle, AC and CB. And so using the definition of a circle, we know they're congruent to each other. We also know that when you have a tangent drawn to, or a radius drawn to a tangent, I should say, that you create a perpendicular relationship. So I know that segment CA, the radius, and segment SA, the tangent, are perpendicular. They form a right angle. And likewise, CB and BS would be perpendicular as well. So what kind of triangle is ACS? It's a right triangle. And what about BCS? For the same reason, it is also a right triangle. And the reason we know is, remember, the radius tangent theorem, which states that a radius drawn to a tangent of the circle is always going to form that perpendicular relationship. So what are we being asked to find in this problem? Well, we talked about that already. For part A, we're trying to find what percent the measure of arc AEB is of the entire circle, which is 360 degrees. We want to know what percent is that. In part B, we're given the percentage, and we're wanting to know the orbiting altitude. So we're wanting to know the length of SE. So number 3 says, what other information might you need to solve this problem? Well, if we are going to find the measure of arc AEB, it would be helpful to know the measure of each one of these arcs, which would mean I need to know these angles. Well, if I knew these angles, I could find those angles, or likewise, right? I need one pair of angle measures, another pair. I know the 90 degree, but I have to know one of the other here so that I know this angle measure, which means I know this arc, which means I could add them together to find the total measure of arc AEB. So I need another angle measure. of triangles ACS and BCS. That's what we need. All right, so we've answered questions 1 through 3. On question 4, it reminds us that AS and BS are tangent segments. So remember, that just means they intersect the circle at only one point apiece. Notice their links as the satellite changes position in this animation. So here we are going to look at moving S around the Earth, and I'll start that over again. So notice the length of the tangents, and as it moved, did you notice it constantly stayed the same? That SA and SB were the same measurement no matter where we moved S. So I'll show you that one more time so you can see that. Okay, so we are noticing that if two tangent segments are drawn from the same or a common external point to the circle, then they are always going to be congruent to each other. SA and SB are congruent. So that is what you are filling in question 4. If two tangent segments are drawn from a common external point to a circle, then the tangent segments are congruent. The tangent segments are congruent. So if we wanted to prove this theorem, what would be the hypothesis and what would be the conclusion? So remember, the hypothesis comes from the if part, but it doesn't include the word if. So our hypothesis is two tangent segments that are drawn from a common external point to a circle. That's the hypothesis. The conclusion is the then part without the word then. So our conclusion is the tangent segments are congruent. Our next question says, how could we use congruent triangles in this proof? So if I wanted to prove that the tangents are congruent to each other, I could prove that these two triangles are congruent. And then, by CP/CTC, prove that that means the tangents are congruent to each other. They are simply corresponding parts of those congruent triangles. So what do we know about the angles and the sides of this diagram? So these are the things that we should know. We've talked about it already. We know the radii are congruent to each other by the definition of a circle. We know we have right triangles because of the radius tangent theorem, that they are perpendicular to each other. That's 2 pieces of information about those triangles, and we know we need a third one in order to prove the triangles are congruent. But notice these 2 triangles have a common side, CS, and so we know that that side is congruent to itself. So that's what we know about the triangle, and that's what we're going to use to actually prove that the triangles are congruent in order to prove that our tangents are congruent to each other. So here is number 5 through 10 in your notes. We're going to complete this proof of the theorem together. And you have answer choices there to use as well. So it says, draw segment SE and the radii, and here you're just naming the radii. So remember, radii are always a segment from the center to a point on the circle, and we have 3 drawn here, but we're really just using 2 of them in our triangles that we're looking at, and those 2 are C to A and C to B. So I'm going to move here so I can drag, hopefully I can drag these. Oh, they're locked, so let's unlock those. Okay, so I'm going to drag the CA and CB. Those are the names of my radii. It says, since radii is drawn to a tangent always creates a perpendicular relationship, we're going to name here what those perpendicular segments are. So the radius CA would be perpendicular to the tangent SA, and the radius CB would be perpendicular to the tangent SB. And so here is the statement that says that. Segments CA and SA are perpendicular, and segments CB and SB are perpendicular. Now remember, if you did not have answer choices here and you are writing this, you do need the segment bars when you're talking about a perpendicular relationship. Leaving them off, remember, represents numbers, and numbers cannot be perpendicular to each other. That doesn't make sense. So now that we have that perpendicular relationship, I could draw right angle symbols here at each one of these angles, which means that both of these triangles are what type of triangles? They are both right triangles. If they contain a right angle, they are right triangles. So here we have two statements. The first one we're making by definition of a circle. So remember, the definition of a circle is the set of all points that are a given distance from a given point. And that's what we use to know that our radii are congruent. So here we're going to say that those radii we identified up here are congruent to each other. Segment CA is congruent to segment CB. We're also going to use the reflexive property to get another congruent statement, and that is that shared side SC. So we know SC is congruent to itself. Now don't forget, we need to mark our figure with this information. So we are going to mark the fact that segments CA and CB are congruent, and we're going to mark the fact that CS is congruent to itself. You always want to mark your figure with what's in your proof so that you can answer the next question, which is the shortcut that proves that those triangles are congruent. Now in this case, we don't have many choices left and we only have one shortcut. But if you were doing this without answer choices, those markings are definitely important to be able to identify that we are indeed using HL. These are right triangles. We're given the hypotenuse congruent to itself. That's the side across from the right angle in each of these. And a leg pair is congruent. So by HL, the triangles are congruent. And we know almost always when we prove triangles congruent and there's more parts of the proof after that, the next step is almost always going to use CP/CTC. Corresponding parts of congruent triangles are congruent. So now that we've proven these triangles are congruent, we know that segment SA and SB are congruent by CP/CTC. And that proves our theorem that if two tangent segments are drawn from a common external point to a circle, then the tangent segments are congruent to each other. So we just proved that theorem, and we have, as a result of that theorem, two corollaries. Now, a corollary is just a statement that is proved that's closely related to the theorem. So it often comes as a result of the theorem. And so we have two statements that we can complete because segment SA and SB are congruent. Now we know that segment CS is an angle bisector. It is bisecting angle ASB. And so if it's bisecting angle ASB, then I know I have these congruent parts as a result. And so that's question 11 in your notes. You know, segment at CS is bisecting angle ASB. And that is this large angle here with vertex S. And so these are my congruent parts. I know angle ASC is congruent to angle BSC. And again, those are corresponding parts of the congruent triangles. So again, that's a result of those triangles being congruent. Okay, so our wrapping up question says, what must be true about two tangent lines to a circle where the points of tangency are the endpoints of the diameter, or a diameter? So I've kind of given you a figure here where we have a diameter going across the circle and we have two tangent lines. So remember, a radius to a tangent line creates that right angle. So I have a right angle formed at both of those points of tangency. And so these lines would have to be parallel to each other, and that uses the fact that these consecutive interior angles are supplementary. They add to 180 degrees. On your assignment tonight, 20.2, one note that you need to make is on number 11, you are not using any numbers. You're using segment names And so you're not going to use the segment bar as a symbol over it because you're actually representing their links instead of a specific number value. So for example, you would use MR, no segment bar, instead of the number 5. So no numbers in number 11.